Hello and welcome. Today I want to show you a visual proof of sum of geometric series that I think is shadowed by how the geometric series and the formula is presented. The typical proof that you'll see everywhere on the internet starts off by generating its geometric sequence, then adding the individual elements in the sequence, continued by proving a formula which gives the result for any sum of a geometric series. Although the proof is completely fine, approaching the sum by adding elements of a geometric series hides the essence of the sum. The sum is all about adding consecutive powers of the same base, and with the formula, we are trying to achieve one universal tool that will work for any base and any power we want to end in. In today's video, I want to show a visual proof by visualizing adding consecutive powers of the same base and going further than what textbooks and other videos goes. To start off, let's look at the sum of consecutive powers of 2, starting from the 0th power and going up to the 7th power. I want to introduce you to a square with side length 1. This square is representing any base raised to the power 0. Throughout the video, I'll call it the unit square, and it will be the starting point for all of our visualizations. Placing 2 of the unit squares on top of each other will create a rectangle whose area is 2 to the power 1. Then, placing 2 of these rectangles side to side creates a square whose area is 2 to the power 2. Throughout the video, I'll call the squares and rectangles constructed by the unit square as objects. We can continue this merging process of objects to generate higher and higher powers of 2. Now, for the sum of these objects, we start by placing our unit square on the lower left-hand corner of the screen. Then we place the object corresponding for 2 to the power 1 right next to it. We continue by placing the next object on top of the stack. After that, we continue placing the objects to the right and to the top of the stack. When we place the object corresponding for 2 to the power 7, we stop adding new blocks. Right now, we are seeing that our sum looks like the object corresponding for 2 to the power 8, only missing a unit square way down in the lower left-hand corner. Adding that unit square completes the object, and our sum plus that extra unit square results in 2 to the power 8. The critical thing about 2 to the power 8 is that if we were to have continued placing objects, we would have placed the object corresponding for it next. We can use this exact method to quickly find any sum of consecutive power of 2 going up to not only to 7, but any positive integer we choose. This sum will equal 1 less than the next power of 2. Okay, let's take a step back and see what we have done. We had this sum of consecutive powers of 2 starting from 2 to the 0 and going up to the 2 to the 7. At first glance, the best option was just to manually add them. However, after visualizing these powers as objects and placing them next to each other, we observed that the sum was 1 less than the next power of 2. After such a discovery, it's only appropriate to try if a method similar will work for other bases than 2. For this, let's walk through the sum of consecutive powers of 5, starting from 0th power and going up to the 3rd power. We'll again construct powers of 5 the same way we did with powers of 2, but instead of placing 2, we'll place 5 objects next to each other. The area of these objects corresponds with powers of 5. We quickly observe that we can place these objects as we did with powers of 2. There are these gaps between objects that we didn't have with powers of 2. Indeed, 1 less than the next power of 5 is not equal to our sum. To equate our sum with the next power of 5, we have to take an additional step that we have completely skipped with powers of 2. This is the object corresponding for 5 to the power 4. Although this is cheating, we'll be placing our objects inside it. We'll place our biggest object corresponding for 5 to the power 3 to the top of the square. Then placing the object representing 5 to the power 2 to the lower right hand corner. And the next 2 objects near the lower left hand corner spaced out in a weird way. It may seem that this complicates the problem further. The additional step we have to take is to place not 1 but 4 of our sums inside. We observe that again we are missing 1 unit square away in the lower left hand corner to complete the object. As with powers of 2, This method will work for any ending power of 5, not just 3. This is just amazing. At first, our special placement seemed to have complicated matters, but in reality, it had a secret structure that helped our problem. Stepping back, we tried to create a formula for the sum of consecutive powers of 5 starting from 0 and going up to the third power. We tried to approach it the same way as we approached powers of 2, but saw that it wasn't as easy as we hoped. By specifically placing the objects, we observed that our sum equals 1 minus the next power of 5, all divided by 4. So we have now found a formula for the sum of consecutive powers of 2 and 5. And in general, the sum of consecutive powers of the same base starting from 0th power and going up to the power of our choice equals 1 minus the next power of the base, all divided by 1 minus the base. The reason is that we can place up to base minus 1 amount of our objects before running into overlapping. The diagram on the screen explains why we have such a case. The formula we have now found is the formula of sum of geometric series, numerator and denominator multiplied by minus 1. There are 1 to 2 little things that I didn't cover in this video, such as what if we were to decide on the initial power. I hope I was able to present my thoughts concisely and effectively. Also, I hope that you have enjoyed watching the video. If you want to write down any feedback about my animations, explanations, or any aspect of the video, please don't fear and write them. Thank you for watching and have a wonderful day.